Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the upcoming exam. So on your screen are all the topics I'm going to go through in this video. This is what you need to know for the final exam. So there isn't actually that much because I'm sure you remember some of these, but let's get into it and I'll try not to make this video too long. So we start off with trigonometry. So remember, trigonometry is used to find unknown sides and unknown angles in right-angled triangles. So you need to know the acronym SOHCAHTOA. Remember, that tells us which ratio to use and which number goes on top, which goes on the bottom. So as I said, we're looking at right-angled triangles. So if I have a right-angled triangle, I can use trigonometry to find an unknown side if I know another side and I know one angle other than the 90-degree angle. So if I tell you I have one 28-degree angle and the hypotenuse is 15, remember the hypotenuse is always the longest side opposite the right angle. If I tell you that, I can find x, which is an unknown side. So firstly, I have to determine which ratio do I use. So x is the side opposite the 28-degree angle because it's facing it. So x is the opposite O and 15 is h, hypotenuse. So the one that involves opposite and hypotenuse is the first one, sine. So that's what it means. S for sine, O for opposite, h for hypotenuse. So I set up my equation like this. Sine of the angle equals, now because O is listed first in SOHCAHTOA, that goes on top. So the opposite goes on top and the hypotenuse on the bottom. So let's now look at this second triangle. So again, I'm finding an unknown side. I have an angle other than the 90-degree angle and another side. So this time, 7.2 is the adjacent because it's next to the 50-degree angle. And again, y is the hypotenuse because it's facing the right angle. It's the longest side. So if I want to solve this equation, which ratio involves the adjacent and hypotenuse? Of course, cos. So cos of angle equals adjacent over hypotenuse. So how do I actually solve these equations? Well, I just need to undo what's been done to x or y. But I'm going to do that slightly different in the blue and black equation. The reason is, in the blue one, x is on top. It's x divide 15. So to get x by itself is simple. I just go x equals 15 times sine 28. So it's really important that you have your calculator in degrees mode or you will get the wrong answer. So to check on the black Casio ones, you should have a little box with a D up the top. It should look something like that. So anyway, if you put that on your calculator to 2 decimal places, you should get about 7.04, okay? And you can just write U for units because we don't know whether it's centimeters or not. So in that situation, I times, but in the black equation, I'm going to divide because the thing I want is on the bottom. So y won't be 7.2 times cos 50, it will be 7.2 divided by cos 50. And again, making sure my calculator is in degrees mode, I get about 11.20 units. Okay, so when the thing you want to find is on top, you multiply. When the thing you want to find is on the bottom, you divide, as we did there, okay? Now, have a think about what your answer should look like. So in the first one, I was finding a shorter side, so the answer should be less than 15, okay? So I know I've done something right. In the second one, I was finding the hypotenuse. The hypotenuse is always the longest side, so I should have got an answer more than 7.2. I did, so I know I did something right. So how do we use trigonometry to find angles? So we can also use trigonometry to find unknown angles. It, fortunately, is quite simple. So you still need to know SOHCAHTOA in order to work out which ratio I use and which one goes on top and which one goes on the bottom. What's easier about finding unknown angles is you don't have to do what I was just talking about, decide if the thing's on the bottom, do I times or do I divide or whatever, okay? This one's a lot simpler. Now, when you're finding angles, you don't use sine, cos, or tan. You use sine inverse, cos inverse, or tan inverse. So usually you need to press like shift and then the sine button or the tan button or whatever. So in this situation, I want to find an unknown angle, which I've called theta. So I have the opposite and adjacent side. So that means I use tan. So I can skip straight to the answer. Instead of using tan, I'm going to use tan inverse. So O comes first, which means opposite goes on top, adjacent goes on the bottom, and that will give me the value of theta. And if you put that on your calculator again, making sure that it is in degrees mode, you should get theta is about 75 degrees to the nearest degree, okay? So that's how you use trigonometry to find unknown sides and angles. We're just going to now quickly look at some applications of trigonometry. So we can use trigonometry to solve problems like this. The angle of elevation to the top of a building from a point 30 meters away is 66 degrees. How tall is the building? So this is a problem in 3 dimensions, but we can use trigonometry to reduce it to a problem in 2 dimensions. So because we're using trigonometry, I need to somehow turn this into a right-angled triangle and find a side or an angle, because that's all we do with trigonometry. So let's start by drawing a diagram. So we've got our building here, and we're talking about a point 30 meters away. Okay, so your diagram, doesn't have to be to scale, okay? Now, what do I mean by angle of elevation and depression? So elevation is the angle going up, depression is the angle going down. So what I'm going to do is just draw some lines here. So it's important we understand the angle of elevation and the angle of depression are always the angle made with the horizontal. So this here is the angle of elevation. This is the angle of depression. What people sometimes do, unfortunately, is they think this one here is the angle of depression and this is the angle of elevation, okay? Don't use that or you will get the wrong answer. So notice I've called both angles theta. Now that's because even though the angle of elevation and depression are different concepts, they always give you the same numerical value. So if the angle of elevation is 66 degrees, which it is in this question, the angle of depression, this one here, will also be 66 degrees. So what we need to do is we need to turn this into a right angled triangle. Of course, we can assume the building will be at right angles to the ground. Now what we have is a triangle that's right angled. We have a side. We have an angle. We want to find another side, and we can do that easily. So again, we use SOHCAHTOA to determine which ratio. So x is opposite, 30 is adjacent. Opposite and adjacent, we use tan. So I get tan 66 equals opposite over adjacent. When the thing you want to find is on top, you multiply. So the height of the building is just going to be 30 times tan 66. And the answer we get, making sure our calculator's in degrees, is about 67.38. So the building is 67.38 meters high. So how cool is that? We've used trigonometry to calculate the height of something that we couldn't really measure, at least not practically. So we've taken a 3D problem and reduced it to a 2D problem. So the last part of trigonometry I need to go through is bearings. So the point of bearings is to quantify the direction in which we've traveled. So remember, of course, we have our compass, we have north, east, south, and west. So if we give the direction I've traveled a number, we can compare that easily. You know, if I said I've traveled northeast, I could have traveled over here or over here. Those two lines may look like they're very close, but if you were a pilot, that is an absolutely massive difference. It could be the difference between life and death, running out of fuel and not running out of fuel. So what we want to do is we want to give each different direction a number. So we look at the angle that is made with the north axis going clockwise. Clockwise is this direction. So if I went on a bearing of 48 degrees, this angle here would be 48 degrees. If I went on a bearing of, say, 130, so up to here is 90, so I would need to go another 40 degrees more. Okay, so 130 degrees, hopefully you see that here, that it is only one possible direction. If I go 130 degrees and you go 130 degrees, we have gone in the exact same direction. So if I wanted to do something like 250 degrees, well, of course, all the way around here would be 270. So 250 would be like over here, and there'd be a 20-degree angle there. So that bearing would be 250 degrees. So these are all true bearings. So we usually put a T after each of them to let people know that we're using a true bearing, even though it's obvious. Okay, so true bearings are just one number, which is an angle made with the north axis in a clockwise direction, and we put a T after them. So we can use these to solve problems in trigonometry. So we'll have a go at this question. I travel 30 kilometers on a bearing of 318 degrees, and I'll find how far north I am of my starting point. So just like with the previous example, what we want to do is somehow get a right-angled triangle and find an unknown side or angle. So if this is our starting point, we can sort of draw a compass here. So 318 degrees means this angle is 318. So it's going to be northwest. So it's going to be like up here somewhere. Okay. So I want to make this into a right-angled triangle. Of course, the axis, the north-south axis, is at right angles to the west-east axis. So this one here was 30 kilometers. Now, a bearing of 318, if this angle here is 318 degrees, how much more do I need to get to 360? Of course, 42 degrees. So that angle in there is 42 degrees. Now, I want to find how far north, so I'm actually finding this length here, x. So this line here in green. So I can do that really easy using trigonometry. So 30 is the hypotenuse of the triangle because it's facing the right angle. X is adjacent to the 42-degree angle. So I have the adjacent and hypotenuse. So I use cos. So I go cos 42 equals adjacent over hypotenuse. So because the thing I want to find is on top, I need to times. So x will be 30 times cos 42. Make sure your calculator's in degrees. You get about 22.29. And of course the answer's in kilometers. So that means I would be 22.29 kilometers north of where I started. So let's have a go at this question here. I travel 8 kilometers east, 15 kilometers south, and I want to know the bearing on which I must travel to return to my starting point. So as I've done in the last few examples, I'll draw a diagram, and I need to have a right-angled triangle somewhere. So I started here, I went 8 kilometers east, and then I went 15 kilometers south. I want to know the bearing I need to travel to return to my starting point. So let's make this a right-angled triangle. So I want to find the bearing on which I must travel. So I need to find this angle here, theta. Now, theta actually won't be the bearing, but I need to know it so I can find the bearing. So, how do I do this? Well, we know how to find unknown angles. Instead of using sine, cos, or tan, I use sine inverse, cos inverse, or tan inverse. So here I have the opposite and adjacent, so I use tan inverse. So theta will be the tan inverse of opposite over adjacent. So the answer I get is about 28.07 degrees. Okay? So I'm not done. This is not the bearing. Because remember, the bearing has to be the angle made with the north axis in a clockwise direction. So if I'm here and I put my compass, the bearing is this angle all the way around there. So actually the bearing, I'll just call that B, will be 360 minus theta, minus 28.07. To the nearest degree, that's 332 degrees true, okay? So remember, bearing has to be the angle made with the north axis in a clockwise direction. So that's all for trigonometry. Let's move on to the next topic of measurement. Now turn our attention to measurement. And we'll start with Pythagoras' theorem. So like trigonometry, it also involves right-angled triangles. Unlike trigonometry, however, it doesn't use the angles. So we can use Pythagoras to find an unknown side when we know the other two sides of the right-angled triangle. So we use it at different times to trigonometry. So we label the sides A, B, and C. It doesn't matter which way around you label A and B. Just label C as the longest side, the hypotenuse. So Pythagoras' theorem is, of course, A squared plus B squared equals C squared. We can rearrange this formula as we like. So if I want to find the longer side, C, it's just the square root of A squared plus B squared. If I want to find a shorter side, which I'll just call A, it's the square root of C squared minus B squared. So note the adding under the square root sign when we're finding the longer side, and the minus under the square root sign when we're finding the shorter side. So as a very quick example, let's say I have a right-angled triangle where I have two sides 5 and 12. So to find x, doesn't matter whether they call it x or c or whatever, it's the longest side, so it will just be the square root of, now I add, square root of 5 squared plus 12 squared, put it straight in your calculator, you get 13. So Pythagoras' theorem can also be useful for solving other problems in measurement, problems involving area, surface area, or volume. So let's have this shape here, and I want to find its area. So this shape here is a trapezium, so it's got one pair of parallel sides. So this side and this side have to be parallel because of the two right angles. So the formula for a trapezium is that area equals h over 2 times a plus b. So note, whenever we see h in the formula in area, surface area, or volume, we always mean perpendicular height. So we actually want this height here, but I don't actually know it from the diagram. So what I can do is I can use Pythagoras to find it. So if I make a triangle here that's right-angled, I can do that. So this side here will be 22 minus 15, which is 7 centimeters. So I can find the perpendicular height, which I'll call x. So to do that, use trigonometry. Because I have a right-angled triangle, I know two of the sides, I need to find the third. So of course, x is now one of the shorter sides, so it's going to be the square root of the longest side minus one of the shorter sides, okay? I minus because I'm finding a shorter side. Put that straight on your calculator, you get 16.58 or thereabouts. So that's not the answer, that's just the perpendicular height. So the total area will be the perpendicular height divided by 2 times the sum of the two parallel sides. So again, putting that on my calculator, I'm going to get about 306.73. So this is area, it will be centimeters squared. So make sure you know how to find the area of shapes like this. You also need to find the area of composite shapes. So let's look at an example of that. So let's have a look at finding the area of the composite shape on your screen. So it's like a rectangle, the first part, plus a quarter of a circle. So if I want to find the area of the whole thing, I just find the area of each individual shape and I add them together. So let's first look at the rectangle. Well, I know the width, but what will be the length? Well, because this here is a quarter circle, the radius will be the same everywhere. So if this side is 10, this side will be 10. Which means this side from here to here in green will be 34 minus 10, which is 24. So the area of the rectangle is just going to be length times width, 24 times 10, easy as. And then I have to find the area of the quarter circle. So the area of a circle is pi times radius squared. If it's a quarter circle, you simply divide by 4. Now, in this particular case, the radius happens to be 10. So I'm going to change r to 10, and that will give me the area of the quarter circle. So that should give us about 78.54. So the total area will be 240 plus 78.54. So about 318.54 Again, it's units squared because I'm talking area. How easy is that? All right, next we're going to look at surface area and volume. So let's look at the total surface area and volume first of this shape here. So this is my poorly drawn rectangular prism. Sorry about the drawing. So when we're looking at total surface area and volume, we're looking at 3D shapes. So this is 3D. It has 3 dimensions. It has length, width, and it has height or depth. Okay, it doesn't matter which way around you call the length, width, or height. The formula will end up being the same. So we'll first look at total surface area. So total surface area, it's basically like saying, if I were to wrap this up in wrapping paper, what would be the minimum area of wrapping paper that I need? Total surface area is just the sum of the area of all the faces of the 3D shape. So a rectangular prism has 6 faces. I just add up all their areas. Now with total surface area, what makes it a bit tricky is, of course, the answer will change depending on whether the shape is open or closed. So for this one, if this was like a box, I would include, say, the top here if it was closed, but not if it was open. So you need to be told that in the question. So I'm now going to calculate the total surface area of this shape, assuming it is closed. So I'm going to find the area of each of the 6 faces and add them together. So firstly, I can look at, say, the front and the back. There'll be another one on the same side, another rectangle that's the same size. So there's 2 lots of 8 by 6 rectangles. Next, I look at the 2 sides. So there's a 6 by 10 rectangle, and there'll be another one on the other side. And of course, I need to include the top here and the bottom. So they will both be 8 by 10. So there's 2 rectangles that are 8 by 10. So if I put that on my calculator, the answer I get 376. Now, because we're talking surface area, it's going to be units squared. So that's 376 centimeters squared. Now, I just want to make a point about whether I had to convert that. So let's say I wanted to convert that to millimeters squared or meters squared. People often mess this up. So we know, for example, that there are 10 millimeters in a centimeter. So normally, if I wanted to go from centimeters to millimeters, I just take it and times by 10. And that would give me millimeters, the number of millimeters. However, when I'm converting square units, I have to square the conversion factor. So there are 10 millimeters in a centimeter, but there are 10 squared or 100 millimeters squared in a centimeter squared. So this would be not 3760, it'd be 37600. Times it by 100 millimeters squared. If I wanted to make this into meters squared, so normally to go from centimeters to meters, I divide by 100 to get it into meters, but because I'm converting square units, I have to square the conversion factor, so it'll be 376 divided by 100 squared, which gives me 0.0376 meters squared, okay? So the rule for conversions, if you're going from a smaller unit to a larger unit, so that's what I did in the second one, started with smaller centimeters, go to a larger one, meters squared, then you divide because there are fewer of the larger unit, and of course the other way. If you start with a larger unit and you go to a smaller one, as I did when converting centimeters to millimeters squared, then you times because there are more of the smaller unit. Okay, let's look now at volume. Volume's actually well, it's a lot simpler than total surface area because you don't have to contend with different faces, whether they're obscured, whether it's open or closed. So the volume for a prism, so this works for any prism, is AH, area of the base, times, as I said before, H is perpendicular height. So for a rectangular prism, you just find the area of the base, 8 times 10, and times by the height. You just times the 3 numbers together. And I would get 480 centimeters cubed. So this time it's cubed because we're in volume. So let's say I wanted to convert that into capacity. So the only difference between volume and capacity is the units. Volume is centimeters cubed, meters cubed, or whatever. Capacity is like liters, milliliters. So the rule for converting to capacity, 1 centimeter cubed is literally the same thing as a milliliter. So if this container holds 480 centimeters cubed, it actually also holds 480 milliliters, which is the same as 0.48 liters, okay? So when you're converting meters cubed and liters, don't be messed up with that. 1 meter cubed is not a liter, it's 1,000 liters. Or if you like, 1 meter cubed is a kiloliter, okay? So make sure you practice with that. Because I don't want this video to be too long, I'm not going to go through any specific examples converting meters cubed and liters, but please let me know if you would like some help explaining it. The next thing I'm going to do, I just need to go through some composite prisms. I want to go through an example of that. Okay, so I have here a composite prism that I got from ck12.org. I can't draw my own composite prisms. I was trying for too long and they just look shocking. So let's look at the surface area and volume of this shape here. So again, surface area is a little more complicated. I can't just find the surface area of each shape and add them together. The reason is, you can see that because I've stuck the half cylinder on top of the rectangular prism, it turns out that there's a face of the rectangular prism that's obscured. I can only count the faces that are exposed, that are not hidden, when I'm finding the total surface area. So what I'm going to do is I'm going to find the surface area of the 5 faces of the rectangular prism that are showing. So the front, this one here, and also the back of the rectangular prism, they're both 9 by 35. Okay? So I'll start with just the rectangular prism. So 2 times 9 times 35. And then on the sides we have 42 by 35, and there's 2 of those. But there's only one 42 by 9. See this one down the bottom, I only include that once because the one at the top is actually not showing. So that is just going to be 1 times 42 times 9. So if I put that on my calculator, I get 3,948. Of course, we are talking centimeters squared because it's surface area. So now I have to find the one for the half cylinder. So this is only half a cylinder, and sorry for my really bad cylinder drawn there. So the total surface area of a cylinder, you need to know the formula. You'll be given a formula sheet, but you'll need to be able to identify that this one here is the surface area of a cylinder. So 2 pi r squared times 2 pi r h. Again, h means perpendicular height, r means radius. So for a normal cylinder where the radius is half of 9, so the radius from here to here is going to be half of 9, which is 4.5, and the height of the cylinder is 42, so that surface area will be 2 times pi times radius squared plus 2 times pi times radius times height. So the thing is, though, because this is not a full cylinder, this is a half cylinder, I need to divide this by 2. So again, just put that on your calculator and I should get about 657.38 centimeters squared. So the total surface area, now I can add these two together, will be this plus this, so that gives me about 4,605.38 centimeters squared. That's the total surface area of the shape, okay? So I couldn't just do the rectangular prism and the cylinder as they were and add them together. I needed to account for the fact that the rectangular prism had one face missing, and also that the cylinder was only half a cylinder. So that's how we do the surface area for that. Now I'm going to rub this out and find the volume. So to find the volume, I can still use the formula AH. Why? Because this is a prism. It has a consistent cross-section. If you like this shape at the back, which is sort of like, a rectangle plus half a circle, that's the same shape and size. It's congruent to the one at the front. This shape has a constant cross-section, therefore it is a prism, therefore I can use the formula volume equals area of base times height. I could actually also, if I wanted, just find the volume of a rectangular prism and add it to the volume of the half cylinder. Remember, because I'm doing volume now, it doesn't matter whether the top of the rectangular prism is shown or not. It doesn't matter whether it's open or closed. The volume of the rectangular prism is the same. So I just want you to know, I could figure this out by finding the volume of the rectangular prism, volume of half cylinder, and adding them together. I'm instead going to find the area of the base and times the height. So I'm going to find the area of the base, which is here. Find that area and times by the perpendicular height. So let's find the area of the base. So I have a rectangle here, which is 9 times 35. And I need to add that to the half circle here, this one here. So as I said before, the radius is 4.5. So this area would be pi times radius squared, but I need to divide by 2 because it's only half a circle. So the answer I get when I put that on my calculator is about 346.80. Now I want to use a few decimal places because I'm going to take this number and multiply it. So I'm going to take that number, which is the area of the base, and I need to times that whole thing by 42, because 42 is the perpendicular height. So when I times it by 42, the answer I get is approximately 14,565.96, and this is centimeters cubed. So of course that would mean that this would hold 14,566, approximately that many milliliters, because a centimeter cubed is a milliliter, and that is about 14.566 liters. That would be its capacity. This is its volume. Okay, so that's how you deal with composite shapes. So our next thing that we're going to move on to is probability. Probability is, of course, assigning to random events a number between 0 and 1 to indicate how likely it is to occur. And of course, if the probability is closer to 1, it's more likely to occur. Probability close to 0, it's more likely that it will not occur. So let's start off with this question here. So class 30 students, 18 brown hair, 8 blue eyes, and 9 neither. I'm going to select a student at random. A is going to be the event they have blue eyes, B is the event they have brown hair, and I'm going to calculate each of these 3 probabilities here. So this question involves the number of elements, in this case students, in 2 categories. Students can have brown hair, blue eyes, both, or neither. So when we're looking at the number of elements in categories, in 2 categories, Venn diagrams and two-way tables are very convenient and effective ways to display the information. So let's first put this in a Venn diagram. So Venn diagrams always look the same. So we have a rectangle here. So all students are within that rectangle. So we have 2 circles, 1 for each category. So there's the blue eye category, which we called A, and the brown hair category, which we called B. So there should be 4 numbers in the Venn diagram. They can be in A only, they can be in both A and B, B only, or neither. So we need to fill in each of those boxes. So note that 18 plus 8 plus 9 is 35, but there were only 30 students. So how is that possible? Well, 35 is 5 too many. However much you've overcounted is how many are in both categories. So we've overcounted by 5, so the only way that's possible is if I counted those 5 in this category and this category, brown hair and blue eyes. So because 18 plus 8 plus 9 is 35, there are going to be 5 students who are in the middle, both blue eyes and brown hair. So what goes in this box here? Well, you might think, okay, well, blue eyes, 8 had blue eyes, I'll put 8 in there. But there's already 5 in the A circle, so we only want another 3 inside it. So there are 3 that have blue eyes but not brown hair. So similarly, there were 18 with brown hair, so there's already 5 in the B circle. I need 13 more, and then there were 9 that had neither. So note, 9 plus 13 plus 5 plus 3 does equal 30. So let's have a look now at a two-way table. So to draw up our two-way table, so we have the possibilities A and not A, that's one way. The second way is B and not B. So note that little dash there means not. A dash means not in A. So there are going to be 4 possibilities here, just like there were 4 possibilities in our Venn diagram. So the 4 numbers that go in each of these cells here are the same 4 numbers that were in the Venn diagram. So you don't really need both a Venn diagram and a two-way table, but I'm just showing you because you might find one a lot easier than the other. We also usually have a row and column for totals in two-way tables. So I'll just extend those, okay? So 4 numbers in yellow come from the Venn diagram. So A and B goes in this category. It's in A and B, and we already figured out that that number was 5. Here, these are the students not A and B, so they did not have blue eyes, but they had brown hair, and there are 13 of those. Over here, we have the students who had blue eyes, but not brown hair, and then there's neither. So we can fill in the totals. They should add up to 30, and they do, so we've done something right. So the same information is displayed in the Venn diagram and the two-way table. Again, they are useful for displaying information about how many elements are in one or both or neither of the 2 categories. So once we've done that, the probability questions become easy. So the first one here, what's that little U sign? Means union, and the way we read it is or. So that's saying what is the probability a student is in A or B? They have blue eyes or brown hair. So note in maths, when we say or, we mean A or B or both. So we have to include both. So we can get that from the Venn diagram or two-way table easy. So these people have blue eyes or brown hair. These do, and these do, but not the 9 outside. Similarly, that corresponds to these people, and these people in the two-way table. All of them have blue eyes or brown hair. So if you add them up, 13 plus 3 plus 5 is 21. So it's 21 over 30. I should simplify my fraction. That is 7 over 10. All right, the next one here. This little symbol means intersection. Read it as and. So that means this here means probability that the student is A and B. That means that they have brown hair and blue eyes. So we're only looking at this region here. So everything in the circle was A or B. Only this little region is A and B. Similarly, this is the cell that corresponds to A and B, students who have blue eyes and brown hair. We can see from both of them there are 5 out of 30 of those students, which is just 1 over 6. So the last one says probability A and not B. Another way to say that is probability A only, the probability they have blue eyes but not brown hair. So A only, we're looking here. These are the students who are in A. They're in the A circle, but not in the B circle. So there are 3 of those out of 30, and we can simplify that to 1 over 10. How easy is that? Now we turn our attention to tree diagrams. So whereas two-way tables and Venn diagrams were useful for displaying information about how many things were in each category or both category or whatever, tree diagrams are used for different purposes. They are used for multi-stage events. So we're talking about events that happen in stages. For example, tossing many coins. Each toss of the coin is a new stage. Or say drawing cards from a deck. So we draw one, that's the first stage. We draw another, that's the second stage. Here we're not talking about how many are in a certain category. So that's why Venn diagrams and two-way tables wouldn't work here. So what do tree diagrams actually do? They just help us list all of the possible outcomes and then find their probabilities. So here we've drawn two cards, one after the other, from a normal 52 card deck, and we're going to find a probability that the two cards are a different suit. So you need to know in the question whether it's with replacement or without replacement. After I took the first card, did I put it back, and can I get it again or not? So that will change the question only slightly. It will just change a few probabilities in the tree diagram. So let's start with replacement. So with replacement means I took the card, I put it back, and I can get it a second time. So we have columns for each of the stages. So here the stages are first draw of the card and second draw of the card. We want to list the outcome and P for probability. So first go, I'm not going to list all 52 cards because I'm not interested in whether it's a king or whether it's jack or anything like that. I'm only interested in the suit. So I'm just going to list the 4 suits. So there is, of course, hearts, diamonds, spades, and clubs. So I can get any one of those 4 on the first go. Now on the second go, of course, I can get them again. I can get 2 hearts, 2 diamonds, or whatever. So if I get hearts, I can get hearts again, or diamonds, spades, or clubs. And similarly for the other 3. Okay, so I've gone and listed now all the possible outcomes. That's what tree diagrams are for. So there should be 16 outcomes because there were 4 on the first go, 4 on the second go. 4 times 4 is 16. So when I do tree diagrams, sometimes you have to write the probabilities on the branches. Now, I don't for this particular example because they're all equally likely. Hearts, diamonds, spades, clubs, they all have a 1/4 chance of coming up. Because I replace the card, each has an equal chance on the second go. So all of these have a probability of occurring of 1/16. They're all equally likely. So what is the probability the 2 cards are a different suit? Well, here I just need to go count the outcomes. So there's 1, 2, 3, 4, 5, 6, and you just keep counting them. And you should note that there will be 12 all up. So there's only 4 outcomes that are not different suits. 1, 2, 3, and the very last one, 4. So if I do the experiment with replacement, the probability the 2 cards are a different suit is just 12/16 or 3/4. But what about if it was without replacement? So this time, I'm going to take a card but not put it back. So we're going to draw a very similar tree diagram. It's actually going to have the same outcomes, but they're just going to have slightly different probabilities. So, on the first go, each of them will have a 1/4 chance of occurring. Okay, nothing's changed there. The thing that will change is the probabilities on the second go. So, if I got hearts the first go, so there are normally 13 hearts in the deck. If I take one out, the probability of getting hearts the second go is going to be 12, because there are 12 hearts left out of 51. So the probability of getting each of the other ones will be 13/51, because there'll still be 13 diamonds and 13 spades and so on. So similarly for diamonds, if I get a diamond the first go, there's only going to be 12 diamonds left out of 51. So the probability of getting a diamond the second go is 12/51, but of getting the other suits is 13/51. Okay, so you're probably getting the idea. So as I said, the outcomes are the same, so I'm just going to list them exactly like I did last time, but the only thing that will change is the probability. So the probability of getting hearts and hearts won't be 1/16 like it was last time. So the probability of getting hearts, how do I figure that out? I times. So I go 1/4 times 12/51. So if you put that in your calculator, you actually get 1/17. So the probability of getting 2 hearts has gone down ever so slightly. If it's without replacement, there's just a slightly less chance you'll get 2 hearts, because if you get hearts the first go, it's taken out. So that'll be the same for all the doubles. So the probability of getting this one will be 1 out of 17 as well. The probability of getting 2 spades will be 1 out of 17, and so on. Okay, but what about the probability of hearts and then diamonds? Well, that will be 1/4 times 13 over 51. So that actually gives us as a fraction 13 over 204. So that would be the same for all of the ones that are not repeated. They'd all be 13 over 204. 1/4 times 13 over 51. Okay, so all of these will be 13 over 204, just to make this a little quicker. Okay, so just note 1 over 16 as a decimal is 0.0625. So that was the probability of getting hearts, diamonds the first go. 13 over 204 is about 0.0637. So about 0.064. So you can see the probability of getting hearts, diamonds has gone up ever so slightly, okay? And of course, that's because if you take hearts out the first go, you've increased the chances you'll get diamonds the second go, okay? So they're very similar, just not quite equal. So what's the probability the 2 cards are a different suit? Well, again, we just look at the outcomes where they are a different suit. So it's not this one, or this one. It's all the others. So there are still 12 of those outcomes. Each of them has probability 13 over 204. So it would just be 12 times 13 over 204. So if you wanted that as a decimal, that is approximately 0.765 to 3 decimal places. So originally, the probability of 2 different suits was 0.75. Now it's gone up to 0.675. So it's gone up slightly, okay? So that's how you do tree diagrams. They are to list all the outcomes and help you find probabilities of multi-stage events. And you need to do them slightly differently, whether they are with or without replacement. If all outcomes at each stage are equally likely, as they were in the first one, we don't need to write probabilities on branches. But if the probabilities are different, as they were in this one here, they were different in the second stage, because not all of the outcomes were equally likely, then we need to write probabilities and multiply them. All right, we now turn our attention to conditional probability. So conditional probability is where we work out the probability that something will happen given that something else will happen. So we're looking here at, say, probability of an event A given B. That's what that line there means, given that. We're saying we know that B's happen. What's the probability A will also happen? So to give you an example, my family has a history of diabetes. So the probability I will get diabetes is higher because my family had diabetes. So the probability that anyone gets diabetes is less than the probability that they have diabetes given that they have a family history of it. Okay? So sometimes other events happening affect the chances that something will happen. So another example could be your maths grade. You have a higher chance of getting an A for the semester if you did well in your first test. The probability that you get an A in maths is slightly higher if you did well in your first test. So the probability that you get an A in maths given that you did well in the first test is higher than the probability that you will get an A in maths. Okay? So let's have a look at how we actually figure this out. So I've drawn a Venn diagram here with just some random numbers. So if I want to find the probability of A given B, what I'm saying is I know that I'm in the B circle. What's the probability I'm also in the A circle? So intuitively, you can see that if I'm in the B circle, there are 5 choices and 3 of them are in the A circle. So the formula we use, because you won't always have Venn diagrams, is that the probability of A given B equals the probability they both happen over the probability that the first one happened. Okay, so whichever one's listed second here, that's the one that goes on the bottom. So I'd get the same answer from the Venn diagram. So A and B is 3. Now there are 10 in total, so the probability of A and B is 3 over 10. Probability of B is 5 over 10. That gives me the same answer, 3 over 5. What would be the probability of B given A? So that's now saying I know I'm in the A circle. What's the probability I'm in the B circle? So that would be the probability that they both happen over the probability the first one happened. Okay, so again, whichever one's second goes on the bottom. So that would be probability of A and B over the probability of A, which is 3 over 7. Okay, so let's look now at an example without a Venn diagram. So let's look at this question here. I pick a card from a deck. What's the probability that it's hearts given that it is red? So now I'm saying I know I picked a red card from the deck. What's the probability it's hearts? So obviously the chance of it being hearts is improved because the card is red. So the probability that the card is a heart given that it's red equals the probability of both of those things happening, that it's a heart and red, over the probability of it being red. So the probability that it's hearts and red, well, that's just a quarter. Because a quarter of the cards are red hearts. In fact, all the hearts are red. The probability the card is red is a half. It can be either red or black. So a quarter divided by a half is a half. Okay, and that makes sense. Because if you get a red card, it's either going to be diamonds or hearts. Has a half probability of occurring. Let's look at one more example. So let's do this question here. I toss 2 coins. What's the probability that the second comes up heads given the first came up tails? So let's just have a look at this intuitively. So if I toss 2 coins, there are 4 possibilities. I could get heads, then heads, heads, then tails, tails, then heads, or tails, then tails. Okay? So the probability that the coin comes up heads second time, I'll call that H2, heads on the second go, given tails on the first go, is the probability that both happen. So the probability that I get heads on the second and tails on the first, so that's the probability here, that's 1 out of 4. But I need to divide that by the probability that I get tails on the first go, and that is 2 out of 4, or a half. So again, a quarter divided a half is a half. So the answer, the probability that the second is heads given the first is tails, is a half. But I want you to notice that that's just the same as the probability that I get heads on the second go. The fact that tails occurred on the first go doesn't change the probability I get heads on the second go. So that is a special case, and we say the events are independent. So if it turns out that probability of A given B is probability of A, what that means is B happening didn't change the probability of A. We say then that A and B are independent. Okay, so there are heaps of examples of independent events. You know, if you roll heaps of die, each outcome is independent. Doesn't matter if you got, 5 6s in a row, the probability that you get a 6 on the next go doesn't change. It's still 1 out of 6. Say like tossing a coin and picking a card from a deck, they are independent. One doesn't affect the chances of the other. That's what it means if 2 things are independent. So now we're going to look at some formula involving independence. So these 2 rules can make probability calculations easier. So if A and B are independent, the probability they both happen, you just multiply the probabilities of each event. So if A and B are not independent, the only other way we have to figure out probability of A and B is rearranging this formula. So the OR rule, which is the second one that I've underlined, says the probability of A or B, add the 2 probabilities and subtract the probability they both happen. So if we're looking at, say, a Venn diagram again, So the probability of, say, A or B, we're looking at this region here, is A plus B. But notice I've shaded in the middle twice. That's why I need to subtract the probability of both, because I will have counted it in A and also in B. So let's look at a few examples where we might implement these rules. So I draw 2 cards from a deck with replacement. What is the probability that I don't get any hearts? So this is the kind of thing we're looking at with tree diagrams. The thing is, I'm only interested in a specific outcome. I just want to know I don't get a heart and then I don't get a heart. Whereas in the previous example, we were looking at the probability that you don't get 2 of the same suits. There were heaps of ways that could happen. You could get, a heart and a diamond, heart and a spade and a clubs, or whatever. So this one, there's only one way it can happen each time. So what's the probability I don't get hearts? So on the first go, the probability I don't get hearts is 3/4. On the second go, the probability I don't get hearts is again 3/4 because the card was replaced. So the probability that that happens on both, that I don't get a heart on the first go and the second go, I can multiply them together because they're independent. What I get on the first go doesn't affect what I get on the second go, so 3/4 times 3/4 is 9/16. Let's look at another example. So let's look at this question here. I roll a die 3 times. What is the probability the first 6 comes up on the third roll? So here I'm just assuming it's a normal 6-sided die. So what I'm saying is, what's the probability I don't get a 6 on the first go, and I don't get a 6 on the second go, and I get a 6 on the third go? So the probability I don't get a 6 the first go is just 5/6. The probability I don't get a 6 on the second roll is 5/6. The probability I do get a 6 on the third roll is 1/6. The probability that all of them happened, I just multiply them together, and I get 25/216, okay? How easy is that? So now I'm going to get rid of the bottom examples, and we're going to look at some questions involving the OR rule. So I pick a card from a deck. What is the probability that is either an ace or a heart? So I know, because it's asking for the probability ace or a heart, not ace and a heart, I'm going to use the OR rule. So the probability of ace or heart equals the probability of an ace plus the probability of a heart, and then I have to minus the probability they both happen. So remember, I can get a card that is an ace and a heart. That's the ace of hearts. So ace and hearts are not mutually exclusive because they can both happen. So the probability that I get an ace, so that is 1/13 or 4/52. Probability of a heart is 1/4. And then, as I said, there's one card that's both of them. So the probability I get the ace of hearts is 1/52. So if you add up all these, you should get 16/52 or 4/13. And that's the question done. So let's do this question. I roll a die and toss a coin. What is the probability that I get heads or a number greater than 4? So again, in maths, or means one or the other or both. So I'm saying, what's the probability I get heads, I get a number greater than 4, or both? So let's have a look. So it would be the probability that I get heads plus the probability I get a number greater than 4 minus the probability that both of those things happen. So the probability I get heads is just half. Probability of a number greater than 4 on the die, so I can get 5 or 6. 2 possible outcomes out of 6. 2 out of 6 is a third. So what's the probability that I get heads and a number greater than 4? Well, they are independent. The outcome of the coin has absolutely no bearing on the outcome of the die. So probability I get heads and a number greater than 4, I multiply these together because they're independent. So if you put that on your calculator, you just get 2/3, which is about 0.67. So I'm just rounding it to 2 decimal places, okay? So sorry this video is getting quite long. we now just need to cover the final topic of statistics, but it should be a lot shorter than the previous 3 topics. Let's start our statistics section by looking at this set of data. So when you have a set of numbers, you should already know how to calculate mean, median, mode, and all that. So the mode is the most common score. So in our set of data, it's 18N25. Okay, you can have more than one mode. So this is bimodal. So the mean, you should remember that's the average. You add up all the scores and divide by how many there are. So the mean and the mode, as well as the median, they are measures of central tendency. They are supposed to tell you the middle point of your data. The range, on the other hand, is different. It's a measure of how spread out the data is. So the range of this data is 36 minus 12, highest minus lowest. Okay, so we took this a step further this year. So you probably already know how to calculate the median, but we then calculate the median of the upper and lower halves of the data called quartiles. But let's first look at the median. So when there are an even number of scores, as there are here, there'll be 2 middle scores. Remember, the data has to be in order to calculate the median. So here, the 2 middle scores are 21 and 23. So the median is halfway between those 2 middle scores. If you don't know what that is off the top of your head, add them up and divide by 2. So the median here would be 22. It's this point in the data. Same number of scores above it as below it. But notice when I find the median, I've sort of divided the data in half. So there are 5 scores in the upper half here and 5 scores in the lower half. The median of the lower half, which is this number here, 18, is called Q1, the lower quartile. So Q1 of this data is 18. So it's the point where there are 25% of scores below it. So if I said that you scored 20% in a test and Q1 was 20%, that means 1/4 of the class scored below your score. So similarly, the median of the upper half, so again in the upper half there are 5 scores, so there'll only be 1 middle score. The median of the upper half here is 25, and we call that Q3. Q2 is actually the median. So Q3 is the point where 25% of scores lie above it. So we looked at the range before. We also learned the interquartile range, IQR. That's just Q3 minus Q1. So here it's 25 minus 18, which is 7. So the difference between range and interquartile range is that the range can be susceptible to outliers. The range will be increased if you have a number that's way below the rest of the scores or way above the rest of the scores. The interquartile range, though, doesn't include the top and bottom scores, so it isn't susceptible to outliers. So that's the only difference between them. So speaking of outliers, we actually came up with a mathematical definition of an outlier. So in class, you would have learnt the mathematical definition. An number is an outlier if it is greater than Q3 plus 1.5 times the interquartile range, or it's less than Q1 minus 1.5 times interquartile range. So this means that we no longer look at the data and say, oh yeah, this number's a long way above. We actually have a definitive way to tell whether or not it's an outlier. So for our data above, so remember Q3 was 25, so Q3 times 1.5 times the interquartile range is 25 plus 1.5 times interquartile range was 7. If you were put that on your calculator, what you get is 35.5. So this is saying a number is an outlier if it is more than 35.5. So this number 36 is in fact an outlier because it's more than 35.5. 28 is not an outlier because it's not more than 35.5. To check outliers that are really small, you do, Q1 minus 1.5 times interquartile range. So here, that would be 18 minus 1.5 times 7, and you get 7.5. So that means for this data, a number will be an outlier if it's less than 7.5. There are no numbers less than 7.5, so there are no outliers at the bottom. So this data set has one outlier. So another thing you need to be able to do is create a box plot. So remember, box plot displays the 5-number summary. So Q0, which is the minimum, Q1, which we said quartile 1, lower quartile, 25% of scores below it, Q2, which is the median, Q3, which is the upper quartile, 25% of scores above it, and Q4, which is the maximum. Those are the 5 things displayed in a box plot. So let's go and draw a box plot for this data here. So we need our number line here, and we'll draw the box plot of this data up here. We'll draw that down below. So Q0 is the minimum, which was 12. So what we do is we put a little dash there. Okay, so then we draw a line up to the next one, which is Q1, which was 18. So 18's here. We draw another dash there. Then Q2, was 22, which will be here. Q3 was 25, which will be about there. And then finally we had 36, which was the maximum. So the box, part of the box plot, so that is the middle 50% of scores. So you join up those into a box, and the other two are called whiskers. So what this does is display the distribution of scores. So because of the way, the definition of what quartiles are, 25% or a quarter of scores will be in this whisker between, in this case, 12 and 22. Then there's 25% in this little box, 25% in this little box, and 25% above. So it's just displaying, the distribution of scores. So it's saying here, we can read off from the box plot that there was, say, 25% of scores, a quarter of scores between 25 and 36. So we're just going to take a quick look now at skewness. So let's consider this box plot here. So it's a very weird shape. So there's only a small distance here between the minimum and Q1, but this still represents 25% of the scores by definition of a quartile. And similarly, there'd be 25% of scores in this narrow range. There'd be 25% or 1/4 of scores in each of the 4 segments. So it turns out this box plot represents skewed data. So let's look at a histogram. What would a histogram look like if I converted the data displayed in the box plot to a histogram? So remember, histogram has bars, frequency along the vertical axis, and score along the horizontal axis. The higher the bar, the more frequent the score. So here we've got a small range, but it still represents the same number of scores as this range from here to here. So what would happen is you'd have scores clustered together with a high frequency closer to the minimum. And that's the same here. There's a low range between the first quartile and the median, right? So there'd be a high frequency of scores closer to the minimum. But when you're getting along here, it's the same number of scores, but it's more spread out. So the bars would be getting lower frequency. They'd be like this as you go on. And the same for this as well. So what's happening is scores closer to the minimum would have a higher frequency. As the scores are increasing, the frequency is going down because there are the same number of scores in this range as there are in this range. So they're more spread out here, as you see in the data there. They're more spread out. So we call this data positively skewed. So make sure you don't get mixed up. It's a bit counterintuitive. You'd probably think that a higher frequency of high scores is positively skewed, but it's actually the opposite. So positively skewed means that scores are clustered towards the minimum, as they are here. These scores are clustered together. There's a lot of them in a small range. So what would it look like if the data was positively skewed or symmetrical? Well, if the data is symmetrical, then so too will be the box plot. So it'll be like the same distance between each of the 4 segments. So that would be symmetrical. So it doesn't have to be perfectly symmetrical for you to call it. So if I were to put that in a histogram, you'd see higher frequency of scores closer to the middle. That's what symmetrical means. You all know what symmetry is. So that's what symmetrical means. So what would a negatively skewed box plot look like? Well, negatively skewed means there's a higher frequency of scores closer to the maximum. So you'd see the opposite of this one here. You'd see a long range for data towards the minimum, but you'd see data towards the top being clustered together. So this plot shows data that is negatively skewed. And if I were to put that in a histogram, if I were to convert the data from the box plot into a histogram, it'd look the opposite to the one in red. You would have a low frequency of scores closer to the minimum, but they would get higher as you get to the maximum, okay? So just make sure you know how to look at a box plot and tell whether the data would be positively skewed, negatively skewed, or symmetrical. So we'll go on with our next subtopic of time series data. So time series data is data where the independent variable, the variable along the x-axis, is time. We're looking at how something changes over time. So the data we're looking at to see whether it changes needs to be numerical itself. So population's a numerical variable because population is a number. You know, country of birth is not a numerical variable. If you ask someone their country of birth, they don't give you a number. So what we're doing is looking at how the numbers change over time. So we can plot this data. So we've got data for 5 years here. I'm just doing a small example, and we'll plot it just like we would plot points on the Cartesian plane. This is a point, and this is a point, and so on. So we draw up our axis. So time is always on the x-axis because it's independent. Time doesn't depend on the population, whereas the population depends on the time. So these little markings here mean that the axes don't start at 0. So if we look at population, the values go from 430 to 580. I don't want to start it and go up 1, 2, 3, 4, all the way up to 580. That'd take too long. So I'm going to start at 425. So this little thing here, breaking the y-axis, just means that it doesn't start at 0. So I'm going to start at 425 and go up in lots of 25s. So it was the same idea for the year. I don't want to start at year 1. That would just be crazy. I want to start at year 2006. So the little break in the axis there says I don't start at 0. So each year is going to get its own point here. Okay? So what we're going to do is graph this so we can see if there is a trend over time. So the first point is 2006, 500. So we just go across to 2006, up to 500, and place that dot. And 2008, 430. So of course, we're not going to be able to get exactly 430. We can just estimate it. It's about there. And we're going to do the same for the other 3 years. So for time series data, when you've plotted all the points, you join them up. You don't do that for normal scatter plots, but you do for time series. So what we're looking at, are there any trends? So it's hard really to identify a trend when you've only got 5 points, but I know you don't want to be here all day and plotting like 30 points. So the overall trend here, we can see it's generally going up. Population is generally increasing. It's not a perfect relationship because it did go down and then went up, but that is the general trend. As time is going on, the population is increasing. If you wrote that answer in a test for this data, you'd accept it full marks. Yay, fantastic. Okay, so now we're going to go on to the very last thing, which is scatter plots. So we just looked at time series data. So that has to have time along the x-axis. So in scatter plots, we're looking at the relationship between two numerical variables. And it's important, they have to be numerical. So again, we couldn't have one axis being country of birth. It's not a numerical variable. So we might be looking at things like the relationship between height and weight, or between shoe size and height, or whatever. We're looking at the relationship between two numerical variables. So in these scatter plots, each dot represents an observation. So let's say this dot here, it would have an x value and a y value, okay? And they would be numerical variables. So it might be, you know, height and weight. So that dot represents a certain value for height, certain value for weight, or whatever. So we need to be able to look at the relationship and determine whether or not it's linear and how strong it is. So when we're saying something is linear, we're saying, can you draw a line through all or most of the dots in the scatter plot? We're saying, does the scatter plot sort of fall in a straight line? Well, this one here, you know, it sort of does, but it's weak. If I draw a line through the middle of the data there, you can see it doesn't do a great job of going through them all. But what's happening is, as this one is going up, as the x value is going up, the y value is also going up, okay? And that's what we mean by positive relationship. So the relationship here between x and y is positive, but it's kind of weak. It's weakly linear. So positive or negative refers to the gradient of the line. So you probably remember from term 1, if a line leans to the right, the gradient's positive, and if it leans to the left, the gradient's negative. So positive gradient means positive relationship. What it means is, if the relationship's positive, it means that as one goes up, the other goes up. If the relationship's negative, it means as one of the variables goes up, the other goes down. So in the first one, as x goes up, y is generally going up weakly, so the relationship is positive and weak. So if I look at the second one with the blue dots, you can see that generally as x is going up, as we're going across, y is actually going down. So I can sort of draw a line through it. It does a better job than the green one, but it's still not great. So here I'm going to say the negative is the relationship, is negative, and it's moderate. So it's negative relationship because as x goes up, y is generally going down. The gradient of the line I drew is negative. And I say it's moderate because it does an okay but not an awesome job of going through the data. The line sort of goes through the data, does an okay job, but not amazing. So in the one with black, you can see that they all pretty much lie in a straight line. So that's a very strong relationship here. It's almost perfect, and it is a positive relationship because the gradient of this line is positive. As the x value is going up, the y value is also going up. So if we look at the last one, you can see the data is scattered all over the place. It's almost random. No matter where I draw a line, it wouldn't do a good job at all of going through the data points. So for the last one, we'd say there's no linear relationship here. So a line just does not do a good job at all of going through any of the data points. We can't say whether the relationship's negative or positive because as x is going up, y, is it going up or down? Well, sometimes it goes up, sometimes it goes down. As I go across here, the y value isn't always going up or always going down, okay? So that's a really poor relationship. So make sure you can look at a scatter plot and determine whether the relationship is linear and whether it's positive or negative. So the very last thing I'm going to go through with scatter plots is how to find the line of best fit. So for this, I've just made up some random data. Let's say there's this maths test we give, and we want to see how everyone goes in it. So to compare them, it'd need to be the same maths test given at the end of year 7, at the end of year 8, or whatever. So I've got some data here. I've got 2 numerical variables. Year is a numerical variable, so is test score. So I can plot these on a scatter plot. So we usually want the independent variable to be on the x-axis. So what year you're in isn't determined by a test score, but your test score is determined by what year you're in. So what we'd want to do is put year along the x-axis, and we want this test score along the y-axis here. So again, I'm going to rule up my axis, and then I'm going to plot each of these 6 points. So note again, I've broken the axis here with that zigzag line to indicate that the axes don't start at 0. There's no point starting at 0 when the lowest year is 7 and the lowest score is 68. So also notice this is data for which I could have fitted a trend line for time series because I might be interested in how the scores go up or down as the years go on. But that would have to be something over time. I might be looking at an individual student. So here, I'm just looking at random years year groups in the same year, which is why a scatter plot is more appropriate. So when we're drawing a scatter plot, we don't join up all the dots. Instead, what we want to do is we want to be able to draw a line that is as close to all of the data points as possible. So the way we do that is as follows. We want to draw the line subject to these two conditions. We need the line to go through at least 2 points so we can find the equation of that line. We also want roughly the same number of points above the line as below the line. Now, it may not always be possible for you to get that exact, but just try as best you can to have the same number of scores above the line as below the line. So let's look again at our scatter plot and let's draw a line that satisfies these two conditions. So notice, if I draw a line through these 2 points, there are the same number of scores above the line, or if you like, to the left of the line, there's 2, as there are to the right of the line. So that's sort of going to be my line of best fit. So that is the line, goes through 2 points, and there are the same number above and below it. So if you draw a line like that, you can find its equation using the techniques that we went through in term 1. So to find the equation of the line, you first find the gradient. So use the 2-point formula for the gradient. And then you substitute m, x and y, so x and y come from one of the points the line went through, into the equation y equals mx plus b. You do that to find b, and then you've got the equation. So let's find the equation of the line that goes through the 2 points in the diagram. So the 2 points it goes through are 972 and 1080. So, to find the equation of this line, gradient equals, so this is like my y2 value, y1, x2, and x1. It doesn't matter which is called point 1 and which is called point 2, as long as x1 is with y1. So this is the point x1, y1, this is the point x2, y2. So gradient, y2 minus y1 over x2 minus x1. So that there just gives you a gradient of 8. So that's step 1 done. So step 2, what I do is I take my equation y equals mx plus b. So I'm going to substitute the gradient for 8 because I just found the gradient was 8. Now I'm going to substitute x and y for one of the points. It doesn't matter which one. I will choose this point here, which is 1080. Sorry, this point here. So what that means is I'm going to substitute x for 10, and I'm going to substitute y for 80. So in this particular example, I get 80 equals 8 times 10 plus b. Of course, 8 times 10 is just 80. So I've got 80 equals 80 plus b. That's a simple equation to solve. Subtract 80 from both sides, you get b equals 0. So the equation of this line is y equals mx plus b. So note, none of the other points were on this line, okay? So the line of best fit doesn't need to go through all of the points. We just needed it to go through 2 so we could find its equation, okay? So we can use that equation to predict values, and I'll show you that now by rubbing out the right-hand side. So now that we have found the equation of our line of best fit, we're going to use this to answer some questions. So according to our line of best fit, what would someone in year 6 score? So year is the x value. So all we're doing is taking our equation y equals 8x and substituting x for 6. So if x is 6, y would just be 8 times 6, which is 48. So our line of best fit predicts that someone in year 6 would score 48. So the next question, if someone scored 34, what year do we predict that they would be in? So here, test score is y, we're substituting y equals 34 into our equation. So we get 34, y equals 8x. We just solve for x like normal. In this case, we divide by 8. We actually get 4.25. Of course, that's not a whole number, but it's closest to 4. So we would predict that if someone scores 34, they would be in year 4. All right, I'm terribly sorry about the very long video, but best of luck studying. Best of luck for the exam. I'm sure you will be fine. This has been the luckiest maths teacher in the world. Have a great day.